Our universe began in a firestorm of pure energy. We are going to tackle 30 of the most profound questions about its formation, a journey that will reshape your understanding of reality itself. By the end, you will have a clear picture of our cosmic origins, from the very first fraction of a second to the distant future. We will explore what triggered the Big Bang and confront the enigma of what, if anything, came before it. How did everything we see emerge from a point of near nothingness? What is your biggest question about the cosmos? What set the entire cosmos into motion? This is the first and perhaps the greatest mystery we face. The Big Bang was not a bomb going off in a dark, empty void. It was the sudden, violent emergence of space and time themselves, an event that created the void and then began to fill it. Picture the entire universe, every galaxy, star, and planet, compressed into a single point of infinite density and infinite temperature. Scientists call this the initial singularity, a state where all the known laws of physics simply break down and cease to have any meaning. Our best theories cannot penetrate that first moment, that point of zero size. It is the ultimate edge of our understanding. So what could possibly cause such a state to suddenly and spectacularly expand? Some physicists point to the bizarre rules of the quantum world, where empty space is never truly empty. It seethes with energy, with tiny particles flickering in and out of existence. Perhaps our entire universe is just one such fluctuation, a quantum bubble that inflated to an unimaginable scale. Other ideas are even more mind-bending. Perhaps our Big Bang was not a true beginning but a rebirth. The cyclic model suggests a universe that expands, contracts, and then bounces back again in an endless cycle. What we call the Big Bang could have been the moment of a great bounce from a previous, collapsing universe. We are left peering back into the first moment of time, searching for a trigger hidden behind a veil of infinite energy, wondering if we are the first chapter in the story or merely the latest. This leads us directly to the next great mystery, one that seems to defy an answer. What existed before the Big Bang? The question itself might be a trap, a trick of language. If the Big Bang was the beginning of time itself, then the idea of a before becomes meaningless. Asking what came before the beginning of time is like asking what is north of the North Pole. Our everyday intuition about cause and effect, where one event always follows another, completely shatters at this point. The equations of general relativity, which describe the cosmos so beautifully, simply break down into infinity at that initial singularity. To even attempt an answer, we need a new kind of physics, one that can marry the vast scales of gravity with the tiny, frenetic world of the quantum. This is the quest for a theory of quantum gravity. Within that theoretical frontier, some truly compelling ideas emerge. One of the most profound is the multiverse. In this view, our Big Bang was not a unique beginning, but a local event. Our entire universe is just one expanding bubble in an infinite, eternal cosmic landscape, a frothing sea of reality where new universes are constantly being born. Another concept suggests a seething, chaotic quantum foam, a realm at the very smallest scale of existence where space and time are not smooth and continuous, but bubbly and unstable. In this foam, tiny universes can pop into existence spontaneously, and our cosmos might be one that, by sheer chance, inflated to a colossal size. These ideas force us to reconsider the nature of reality itself. They challenge our most basic assumptions about time and causality, suggesting that our universe is not the entire story, but merely one chapter in a book with no beginning and no end. If our universe was born from a singularity, how did it grow to such an immense and uniform scale so quickly? A mere fraction of a second after that initial moment, something truly spectacular happened. The cosmos underwent a growth spurt of unimaginable speed, a period known as cosmic inflation. For a fleeting instant, space itself expanded faster than the speed of light. inflating a subatomic speck of primordial energy into a region vastly larger than our entire observable universe. This was not the steady expansion we see today, but an explosive, exponential burst that set the stage for everything to come. This single idea, cosmic inflation, solves two of the most stubborn puzzles in cosmology. The first is the horizon problem. Look at the cosmic microwave background, the ancient afterglow of the Big Bang. No matter which direction you point a telescope, this radiation is almost exactly the same temperature. But in a universe expanding at a steady rate, there simply has not been enough time for heat to flow from one distant region to another, balancing everything out. It is like walking into a vast concert hall and finding that every single seat, even those on opposite sides, is exactly the same warm temperature, even though the heaters are too far apart to have ever communicated. Inflation fixes this by proposing that the entire observable universe was once a tiny, connected patch that had ample time to even out its temperature before being suddenly and violently stretched to cosmic proportions. The second puzzle is the flatness problem. The geometry of our universe appears incredibly flat, meaning parallel lines stay parallel, and the angles of a triangle add up to exactly 180 degrees. For this to be true after billions of years of evolution, the density of the early universe had to be fine-tuned to a breathtakingly precise value at its birth. The slightest deviation would have resulted in a cosmos that either collapsed back on itself immediately or expanded into a thin, cold emptiness. Inflation naturally produces this flatness. Imagine taking a tiny, wrinkled crinkle in a vast sheet of rubber and then stretching that sheet to the size of a galaxy. That one tiny section you're looking at would appear perfectly flat. The driving force behind this incredible expansion is thought to be a mysterious field that permeated the early cosmos called the inflaton field. This field possessed a peculiar kind of energy that acted like a kind of anti-gravity, pushing space apart with tremendous force. Then, in a moment known as reheating, this field decayed. Its immense pent-up energy was released in a spectacular firestorm, flooding the universe with the hot, dense soup of particles and radiation that would eventually coalesce into the first atoms, stars, and galaxies. The stage was finally set, but the next question is just as fundamental. What was the universe made of in its first fleeting moments? That spectacular firestorm of reheating filled the cosmos with a seething, blinding ocean of energy and elementary particles. For nearly 400,000 years, the universe remained too hot and dense for light to travel freely. Electrons and protons were locked in a frantic dance, constantly scattering the intense radiation that filled every point in space. But then, a profound transition occurred. As the cosmos expanded and cooled, it finally reached a temperature where electrons could combine with protons to form the first stable, neutral atoms. In that pivotal moment, the fog lifted. The radiation that had been trapped for eons was suddenly set free, streaming across the universe in every direction. This is the cosmic microwave background, the oldest light we can ever hope to see. It is the universe's baby picture, a fossil imprint from its infancy. This ancient glow was discovered entirely by accident in the 1960s by two radio astronomers, Arno Penzias and Robert Wilson. They were troubleshooting a persistent, annoying hiss in their giant horn antenna, a noise that remained constant no matter where they pointed it. After meticulously cleaning out pigeon droppings from the antenna and ruling out every other possible source, they realized the signal was real. It was coming from the cosmos itself, a faint microwave whisper permeating all of space. They had stumbled upon the cooled remnant of the universe's fiery birth, a discovery that earned them the Nobel Prize and provided the smoking gun evidence for the Big Bang theory. Today, that afterglow is incredibly cold, just a few degrees above absolute zero. Its original high-energy light stretched into the microwave part of the spectrum by the relentless expansion of the universe over billions of years. But its true treasure lies not in its uniform temperature, but in its tiny imperfections. When we map this background with incredible precision, using satellites like Planck, we see that it is not perfectly smooth. There are minuscule variations, tiny ripples in temperature that represent regions of slightly higher and lower density in the early cosmos. These ripples are the seeds of destiny. They are the gravitational blueprints for everything that would follow. The slightly denser patches, imprinted by quantum fluctuations from the inflationary epoch, had just enough extra gravity to begin pulling in surrounding matter. Over hundreds of millions of years, these tiny overdensities grew, snowballing into vast cosmic structures. The great web of galaxy clusters and the vast empty voids between them were all mapped out in those first tiny wrinkles. By studying these patterns with exquisite detail, scientists can read the cosmic microwave background like a history book. It tells us the exact age of the universe, down to a stunning degree of accuracy, 13.8 billion years. It reveals the precise composition of the cosmos, how much is ordinary matter, how much is the mysterious dark matter, and how much is the even more enigmatic dark energy driving the expansion to accelerate. It even confirms the geometry of the universe, showing it to be flat, just as the theory of inflation predicted. This faint whisper from the dawn of time continues to be our most powerful window into the origin and fate of everything we see. Those tiny ripples in the cosmic afterglow set the stage, but the universe was still a simple and elemental place. Within the first 3 minutes, a crucial forge was lit, creating the very first building blocks of matter. This brief and explosive period is known as Big Bang nucleosynthesis. The entire cosmos was still an unimaginably hot and dense furnace, a seething plasma of fundamental particles. Protons and neutrons, the constituents of atomic nuclei, were bouncing around in this frenzied inferno. As the universe expanded and cooled, it reached a temperature where these particles could begin to stick together. Protons, which are single, positively charged hydrogen nuclei, started to capture neutrons. A proton and a neutron fused to form a deuterium nucleus, a heavy form of hydrogen. This was the crucial first step. Once deuterium existed, it could rapidly collide with other protons and neutrons, forming helium. For a few fleeting minutes, the early universe acted like a colossal fusion reactor, cranking out atomic nuclei at a furious pace. But this cosmic factory had a very short production run. The universe was expanding and cooling too quickly. After about 3 minutes, the temperature and density had dropped so much that the positively charged nuclei could no longer overcome their mutual electrical repulsion. The frantic fusion process slammed to a halt. The result was a universe composed of about 75% hydrogen and 25% helium by mass, with only the tiniest trace amounts of lithium. Every other element in the periodic table, from the carbon in our cells to the oxygen we breathe, simply did not exist yet. The cosmos was a vast, primordial cloud of the two lightest elements. This prediction is one of the most stunning successes of the Big Bang theory. When astronomers measure the chemical composition of the oldest stars and the most distant, pristine gas clouds, they find exactly this ratio, 75% hydrogen to 25% helium. It is a perfect match, a cosmic fingerprint left over from the universe's first 3 minutes. This agreement between prediction and observation is so precise that it locks in our understanding of the early conditions. It tells us how many protons and neutrons were present and how rapidly the cosmos was expanding during that critical epoch. For billions of years, the universe would remain a simple place, a dark expanse of hydrogen and helium gas, waiting for gravity to pull together the first stars and light the fires that would forge the rest of the periodic table. But for all its power, that primordial forge of hydrogen and helium faced a monumental problem. The gravity from ordinary matter alone was simply too weak to build the vast cosmic structures we see today. The seeds were there in the cosmic microwave background, but they needed a hidden form of mass, a secret ingredient to provide the gravitational muscle for galaxy formation. This brings us to one of the most profound mysteries in all of science, the enigma of dark matter. We now know that the atoms making up stars, planets, and us constitute less than 5% of the total content of the universe. A full quarter of the cosmos is made of something else entirely, a substance that is fundamentally alien. Dark matter is invisible. It does not emit, absorb, or reflect any form of light. It is completely transparent, passing through our most powerful telescopes undetected. So how can we possibly know it is there? The evidence comes from watching how it moves the universe around it. In the 1930s, astronomer Fritz Zwicky was studying the Coma Cluster, a massive group of galaxies. He measured how fast individual galaxies were orbiting the cluster's center and made a startling discovery. They were moving far too quickly. The combined gravitational pull from all the visible stars and gas in the cluster was far too weak to hold these speeding galaxies together. The entire system should have flown apart long ago. The only explanation was that the cluster was filled with a huge amount of unseen mass, a dark gravitational glue holding everything together. Decades later, Vera Rubin provided even more compelling proof by studying the rotation of individual spiral galaxies. She found that stars at the outer edges of galaxies orbit just as fast as those near the center. This defies the laws of gravity as we know them. In our solar system, planets farther from the sun move more slowly. If a galaxy were made only of the stars we see, its outer stars should be crawling along. The fact that they race around implies that each galaxy is embedded within a gigantic, invisible sphere of matter, a dark matter halo that extends far beyond the visible edge of the galaxy. We see this ghostly gravitational influence everywhere. Massive clusters of galaxies act like cosmic lenses, bending the light from even more distant galaxies behind them. This effect, called gravitational lensing, creates distorted arcs and multiple images of the same background object. When astronomers map this bending, they find that the amount of mass required to warp space so dramatically is many times greater than the mass of all the visible galaxies in the cluster. The true skeleton of the cluster is made of dark matter. This invisible scaffolding was absolutely crucial in the early universe. After the Big Bang, ordinary matter was a hot, pressurized plasma, pushing back against gravity with the intense force of radiation. Dark matter, however, is thought to be cold and sluggish, unaffected by light. It was free to start clumping together immediately under its own gravity, forming vast, invisible webs and dense halos long before atoms could even form. These dark matter wells became the gravitational anchors for the future. They pulled in the swirling clouds of hydrogen and helium gas, providing the concentrated gravity needed to overcome the gas's pressure and turbulence. Without dark matter, the slight ripples from the Big Bang would have taken far too long to grow. Galaxies might never have formed, or they would have been small, faint, and rare. Dark matter provided the cosmic infrastructure, the hidden architecture upon which the luminous universe of stars and galaxies was built. Every majestic spiral and colossal cluster we see today is just the visible tip of a much larger, darker iceberg. This invisible scaffolding of dark matter shaped the cosmos, but another, even more mysterious force was lying in wait, preparing to seize control of the universe's destiny. The story of our cosmos took its most unexpected turn in the late 1990s. For decades, astronomers had assumed that the expansion of the universe, set in motion by the Big Bang, must be slowing down. The mutual gravitational pull of all the matter in the cosmos, both light and dark, should have been acting like a cosmic brake, gradually decelerating the great outward rush. Two rival teams set out to measure this deceleration by studying a special kind of stellar explosion, a Type 1, a supernova. These events are cosmic standard candles exploding with a known, predictable brightness. By carefully observing how dim they appeared in distant galaxies, scientists could calculate their exact distance. By then measuring how much the light from these supernovae was stretched or redshifted by the expansion of the universe, they could determine how fast the universe was expanding when that star exploded billions of years ago. They were gathering data to answer one simple question: how much has the expansion slowed? The answer they found was utterly shocking. The distant supernovae were fainter than they should have been. This could mean only one thing: these ancient stars were farther away than anyone had predicted. The expansion of the universe was not slowing down at all. It was speeding up. Something was actively pushing galaxies apart, a force with a repulsive gravity that grew stronger as the universe expanded and became emptier. This discovery was so bizarre and counterintuitive that it earned the teams the Nobel Prize in Physics. The mysterious agent causing this anti-gravity effect was named dark energy. Today, we know dark energy is the dominant component of the universe, making up a staggering 68% of its total energy content. It is the primary force shaping the cosmos on the largest scales, and its nature is one of the greatest puzzles in all of science. The leading candidate for dark energy is the cosmological constant, an idea that Albert Einstein first proposed and then later called his greatest blunder. He introduced it as a fudge factor, a repulsive force embedded in the fabric of empty space itself, to keep the universe static and prevent it from collapsing under gravity. When the universe was found to be expanding, he discarded the idea, but now it has made a spectacular comeback. If dark energy is the cosmological constant, it means that empty space is not nothing. It possesses a fundamental, intrinsic energy. As the universe expands and more space comes into existence, this vacuum energy increases, leading to a repulsive force that drives the acceleration. The cosmological constant is a property of space itself, constant and unchanging through time. But is it really that simple? Another possibility is that dark energy is not constant at all. It could be a dynamic field, similar to the inflaton field that drove the early period of inflation, but vastly weaker. This concept, sometimes called quintessence, suggests that the strength of dark energy could change over time, perhaps even decaying away in the distant future. The implications for the ultimate fate of the universe are profound. If dark energy is a true cosmological constant, the acceleration will continue forever. In tens of billions of years, all galaxies outside our own local group will be pushed away by the accelerating expansion, their light stretched beyond the visible spectrum until they vanish from our sky entirely. The universe will become a cold, dark, and lonely place, with island galaxies drifting in an ever-widening emptiness. If dark energy is dynamic, however, the future could be dramatically different, perhaps even ending in a catastrophic reversal. For now, dark energy remains a deep enigma. Its existence tells us that our understanding of gravity, space, and the vacuum is profoundly incomplete. It is a dominant force that we cannot see, barely understand, and yet one that holds the key to the final chapter of our cosmic story. After the cosmic dawn faded into darkness, the universe entered its longest and most silent chapter. For millions of years, the cosmos was a vast, featureless sea of hydrogen and helium gas, cloaked in an impenetrable blackness. This was the cosmic dark ages, a time before the first stars, when the only light was the fading afterglow of the Big Bang, steadily stretching into invisibility. Yet within that profound darkness, the faint blueprints of creation were slowly, inexorably coming to life. The tiny ripples imprinted in the cosmic microwave background, amplified by the gravitational pull of invisible dark matter halos, were beginning to pull matter together. Vast clouds of primordial gas, drawn by the irresistible tug of these dark matter wells, started to coalesce into the first protogalaxies. These were not the majestic spirals we see today, but messy, chaotic clumps of dark matter and gas, the raw, unformed embryos of future galaxies. Deep within these swirling clouds, the next great transformation was about to begin. Gravity began to work on the gas itself, pulling dense knots of hydrogen and helium inward. As these pockets collapsed, their cores grew hot and dense under the mounting pressure. For the first time since the Big Bang's initial fireball, nuclear fusion was about to be rekindled in the heart of a star. The first generation of stars, known as Population 3 stars, were unlike anything that exists today. Born from pure hydrogen and helium, with no heavy elements to help them cool and fragment, they grew to monstrous sizes. These stellar titans were likely hundreds of times more massive than our Sun, burning at ferociously high temperatures and shining with a brilliant bluish-white light. Their lives were spectacularly short, blazing for only a few million years before meeting a violent end. But in their brief existence, they utterly transformed the cosmos. Their intense ultraviolet radiation blasted through the surrounding gas, stripping electrons from atoms and beginning the process of reionization. This was the end of the Dark Ages. The universe's neutral hydrogen fog was burned away, and the cosmos became transparent once more, this time filled with the light of countless new stars. The death of these first stars was as important as their birth. Their cataclysmic supernova explosions were universe-altering events. In their fiery hearts, nuclear fusion had forged the first heavy elements beyond helium, carbon, oxygen, nitrogen, and traces of others. These newly minted atoms were then scattered across space by the supernova blasts, polluting the pristine gas clouds with the seeds of future chemistry. This was the first cosmic pollution, and it was essential for everything that followed. The next generation of stars that formed from this enriched gas could be smaller, cooler, and far more stable. And around these second-generation stars, the heavy elements could now clump together to form the first dust grains, rocks, and eventually planets. The ignition of the first stars did not just light up the darkness, it forged the very elements that would one day make life possible. These stellar titans not only lit up the cosmos but also forged the seeds of the most extreme objects in the universe. When the most massive of those first stars died, they did not just explode, they collapsed. Their cores, no longer supported by the outward push of fusion, imploded under their own immense gravity, crushing down into points of infinite density and creating the very first black holes. These primordial black holes were likely the building blocks for the cosmic behemoths we find today, the supermassive black holes that lurk at the heart of nearly every large galaxy, including our own Milky Way. Weighing in at millions or even billions of times the mass of our Sun, these monsters are not mere residents of their galaxies. They are active participants in a grand cosmic dance, their growth intimately tied to the evolution of the galaxy itself. This is the theory of co-evolution, a powerful idea that suggests a black hole and its host galaxy grow up together, locked in a complex gravitational and energetic relationship. The evidence for this is etched into the fabric of galaxies. Astronomers have found a remarkable correlation between the mass of a galaxy's central bulge of stars and the mass of its supermassive black hole. The bigger the bulge, the bigger the black hole. This is not a coincidence. It points to a shared history of growth, where the same processes that feed the galaxy's stars also feed the central monster. But how does this relationship work? The key lies in the concept of feedback. For a long time, it was a puzzle why giant elliptical galaxies, for instance, are not still forming stars at a furious rate. They contain vast reservoirs of cold gas, the raw material for new stars. The answer appears to be the supermassive black hole. When a black hole is actively feeding, pulling in vast amounts of gas and dust, it does not quietly consume its meal. The infalling material swirls into a superheated accretion disk, glowing with the intensity of billions of stars. This active galactic nucleus can unleash colossal jets of energy and matter, shooting out from its poles at nearly the speed of light. These jets and the intense radiation pouring from the disk blast through the surrounding galaxy. They heat the interstellar gas, preventing it from cooling and collapsing into new stars. In the most extreme cases, they can even blow the gas clean out of the galaxy altogether. This black hole feedback acts as a cosmic thermostat, a self-regulating mechanism for the galaxy. If too much gas flows in, it triggers a feeding frenzy in the black hole, which then unleashes a blast of energy that shuts down the gas supply, effectively putting a brake on the galaxy's growth. This explosive cycle explains why we do not see galaxies growing indefinitely. The supermassive black hole, through its violent outbursts, helps shape the galaxy's structure, determines its final size, and ultimately dictates its star-forming future. The ghost of these ancient eruptions can still be seen today in the form of gigantic, empty bubbles in the hot gas surrounding galaxies like our own, silent testimony to a past era of violent activity from the central engine. So these gravitational pits are not just destructive abysses, they are fundamental architects, their powerful influence woven into the very fabric of the cosmic structures we see across the universe. The destiny of the cosmos hinges on a delicate balance between two opposing forces, the relentless outward push of dark energy and the inward pull of gravity from all matter. Our ultimate fate depends entirely on which of these titans wins the long-term war. The leading contender, based on our current best data, is a scenario known as the Big Freeze or heat death. In this future, dark energy remains constant, and the expansion of the universe continues to accelerate forever. Over trillions of years, the last stars will burn out, their fuel exhausted. Galaxies will drift apart, their light stretched into undetectable radio waves until the sky goes completely black. Even the black holes will eventually evaporate over almost unimaginable timescales through a process known as Hawking radiation. The universe will reach a state of maximum entropy, a final, uniform temperature just a fraction of a degree above absolute zero. It becomes a thin, cold, and utterly dark sea of isolated particles, where no energy can be harnessed, no structure can form, and no further change is possible. It is not a dramatic explosion, but a slow, quiet fading into eternal stillness. But what if dark energy is not constant? Another terrifying possibility is the Big Rip. If the repulsive force of dark energy grows stronger over time, its push would eventually overcome all other forces in the universe. First, it would tear apart galaxy clusters, then individual galaxies. As the acceleration becomes infinite, it would rip stars from their solar systems, planets from their stars. In the final horrific moments, atoms themselves would be torn asunder, and finally, the very fabric of space-time would be shredded. The universe would end in a catastrophic, violent dissolution of all matter. There are also more cyclical visions of our fate. The Big Crunch is the classic mirror of the Big Bang. If the density of matter in the universe were high enough, gravity would eventually reverse the expansion. After slowing to a halt, the cosmos would begin to collapse inward upon itself. Galaxies would rush together, temperatures would soar, and the universe would end in a fiery implosion, perhaps crushing back down into a singularity. This leads directly to the idea of the Big Bounce, a cyclic model where the universe undergoes an endless series of expansions and contractions. Each Big Crunch gives birth to a new Big Bang in an eternal cosmic cycle of death and rebirth. The fate of our universe is not yet written. The deciding factor is the precise nature of dark energy and the ultimate geometry of the cosmos. Our most precise measurements currently point toward the Big Freeze, a quiet and cold end. Yet a sliver of uncertainty remains, leaving open the possibility that the cosmos is destined for a far more dramatic finale. This leads us to a question that probes the very nature of physical law. Could the fundamental constants that govern our universe, the very rules of reality, change over time? The ultimate fate of our universe hinges on the precise values of its fundamental constants, a set of numbers that seem almost miraculously fine-tuned for our existence. But what if this cosmic perfection is not a miracle, but a simple matter of statistics? This line of thinking leads us directly to one of the most mind-expanding ideas in all of science, the concept of the multiverse. The multiverse is not a single theory, but a spectrum of ideas suggesting that our universe is just one of many, perhaps even an infinite number of parallel realities. The first and most grounded version of this idea arises directly from the theory of cosmic inflation. We already know that our observable universe is just a tiny patch within a vastly larger cosmos. A level 1 multiverse simply takes this to its logical conclusion. If space is infinite and matter is distributed more or less randomly, then every possible configuration of matter must repeat somewhere. Far beyond our cosmic horizon, there could be regions of space where an exact copy of you is listening to an exact copy of this script, while in others, the Earth never formed or the laws of physics are subtly different. This is not science fiction, but a direct implication of an infinite, post-inflationary space. Then we have the level 2 multiverse, which is even more profound. Eternal inflation, a variation on the standard inflationary model, suggests that the process of space bubbling into new universes never stops. In this eternal froth, each separate bubble universe can have its own unique set of physical laws and constants. The force of gravity might be stronger in one, the speed of light slower in another. In this vast cosmic landscape, most of these universes would be sterile, incapable of forming atoms or stars. But in a rare few, like our own, the numbers would line up perfectly to allow for galaxies, planets, and life. Our existence in such a hospitable universe would then be no more surprising than a lottery winner being amazed they hold the winning ticket, ignoring the millions of other tickets that lost. String theory, a candidate for a theory of everything, adds another layer to this. It suggests there could be a staggering number of possible stable configurations for the extra dimensions it proposes, perhaps 10 to the 500 different versions. Each of these configurations would correspond to a universe with a different vacuum energy and different physical laws, creating a vast string theory landscape that aligns perfectly with the level 2 inflationary multiverse. The most controversial version is the level 3 multiverse, which emerges from the strange rules of quantum mechanics. According to the many worlds interpretation, every time a quantum event has multiple possible outcomes, the entire universe splits into branches, each one realizing a different possibility. In one branch, a radioactive atom decays, and in another, it does not. This implies a constantly proliferating tree of reality, where every possible history actually plays out in some parallel world. The scientific status of the multiverse is hotly debated. Is it a testable scientific theory or an untestable metaphysical idea? Proponents argue that if a multiverse model, like eternal inflation, makes specific predictions about the statistical distribution of constants we should observe in our own universe, and those predictions match our data, then it is indeed science. Critics counter that if we can never interact with or observe these other universes, the idea falls outside the realm of empirical science. The implications are staggering. If true, the multiverse would be the ultimate Copernican revolution, demoting our universe from a unique creation to a single page in an infinite library of realities. It challenges our very definition of reality and forces us to ask, in a cosmos of infinite possibilities, what does it even mean for something to be real? Time itself is perhaps the most fundamental ingredient in our reality, yet its origin is shrouded in the same initial fireball that birthed the cosmos. According to Einstein's theory of general relativity, time is not a separate, absolute backdrop. It is intimately woven together with the three dimensions of space into a single, four-dimensional fabric called spacetime. This fabric can be stretched and warped by matter and energy, and crucially, it expanded into existence from the Big Bang singularity. This leads to a startling conclusion. Time did not simply begin to pass within a pre-existing void. The very container of time was created in that first explosive moment. The concept of a before the Big Bang becomes problematic, even nonsensical, because there was no time for a before to exist in. Our language and intuition, built around a linear flow of cause and effect, completely fail us at this boundary. Our current laws of physics break down entirely at the moment of the initial singularity. To peer further back, we must venture into the realm of quantum gravity, to the Planck epoch, a period so brief it is almost beyond comprehension, the first 10 to the minus 43 seconds of the universe. At this scale, the smooth fabric of spacetime is thought to dissolve into a chaotic, foamy quantum uncertainty. Here, time and space themselves may lose their definite nature, fluctuating wildly. This is the ultimate edge of our scientific understanding, a wall we cannot yet see beyond. Some theories attempt to smooth over this sharp edge of creation. The no-boundary proposal, developed by James Hartle and Stephen Hawking, offers a profoundly different vision. It suggests the universe has no initial boundary in time, much like the North Pole has no latitude north of it. In this model, if you could run the cosmic film backwards, time would gradually transform into a dimension that behaves more like space. The Big Bang singularity vanishes, replaced by a smooth, geometrical cap, a rounded off beginning with no sharp edge and no need for a boundary condition. It is a universe that simply is, without a definitive moment of creation in the way we typically imagine. This idea, while mathematically elegant, is not the final answer. It underscores the reality that a full understanding of time's origin is inseparable from a complete theory of quantum gravity, a framework that can seamlessly unite the large-scale world of general relativity with the tiny, probabilistic world of quantum mechanics. Such a theory would tell us whether time truly emerged from a timeless state, or if it has always existed in some form beyond our current comprehension. The beginning of time remains one of the deepest puzzles, a mystery locked within the first fleeting whisper of the cosmos. A perfectly balanced universe would have been a cosmic stillbirth. The Big Bang should have forged matter and antimatter in perfectly equal amounts. For every proton born, an antiproton should have emerged. For every electron, a positron. These particle-antiparticle pairs are perfect mirror images, destined to annihilate each other on contact in a flash of pure energy. Had this perfect symmetry held, every particle in the early universe would have found its antimatter twin. The entire cosmic inventory would have been converted back into radiation, leaving behind a vast, empty expanse of light with no atoms, no stars, no planets, and certainly no us. The fact that we exist at all is proof that this symmetry was broken. Somewhere in the first fleeting moments, a fundamental rule was bent, allowing one extra particle of matter to survive for every billion annihilations. That one in a billion remnant is everything we see, a cosmic ghost town built from the ashes of a near-total mutual destruction. This mystery of how our universe became dominated by matter is known as the problem of baryogenesis. In the 1960s, Russian physicist Andrei Sakharov outlined the three essential conditions needed to create this cosmic imbalance. The first is baryon number violation. A baryon is a heavy particle like a proton or neutron, the stuff that makes up atomic nuclei. For matter to win out, there must be a physical process that does not conserve the total number of baryons, a rare reaction that can create more matter than antimatter. The second condition is a violation of both C and CP symmetry. C symmetry, or charge conjugation, means the laws of physics should be the same if you swap every particle with its antiparticle. CP symmetry is even subtler. It means the universe should behave the same if you simultaneously swap particles for antiparticles and mirror the coordinates of space, turning left into right. We have observed tiny, precise violations of CP symmetry in the decay of certain exotic particles. It is as if the universe has a tiny, built-in preference for spinning left-handed over right-handed or for matter over antimatter. The third Sakharov condition requires that these asymmetric processes occurred out of thermal equilibrium. In the ultra-hot, uniform soup of the very early universe, any slight imbalance would have been instantly wiped out. There had to be a moment of cosmic transition, like water freezing into ice, where the rules changed rapidly enough to lock in a tiny excess of matter before it could be erased. While these three conditions give us a theoretical roadmap, the exact physical process that fulfilled them remains one of the biggest unsolved problems in physics. Our most powerful tool for hunting this cosmic culprit is the Large Hadron Collider. By smashing protons together at velocities approaching the speed of light, we recreate the searing conditions of the early universe. Scientists meticulously analyze the debris from these collisions, searching for any subtle deviation, any particle that decays slightly more often into matter than antimatter. They are looking for the faint echo of that first critical cosmic crime, the original event that tipped the scales and made our material world possible. That 1 in a billion victory for matter set the stage for everything, but the grand arena of the cosmos itself has a fundamental geometry. The shape of the universe is not an abstract curiosity, it is a direct reflection of its total contents and its ultimate destiny. There are three primary possibilities for this cosmic geometry, each dictated by the precise density of all the matter and energy in the cosmos. If the density is exactly at a critical value, the universe is flat. This is the familiar geometry we learn in school, where parallel lines never meet and the angles of a triangle add up to exactly 180 degrees. A flat universe is most likely infinite in extent, stretching on forever in all directions. If the density is higher than this critical value, the universe curves in on itself like the surface of a sphere. In this closed, spherical universe, parallel lines would eventually converge. You could, in theory, set off in a straight line in a spacecraft and after an unimaginably long journey, return to your starting point from the opposite direction. This cosmos would be finite but without any edge, a perfectly self-contained reality. The third possibility is a hyperbolic or open universe, which occurs if the density is too low. Here, space would be curved outward like an infinite saddle. Parallel lines would diverge, racing away from each other, and the angles of a triangle would add up to less than 180 degrees. So how can we possibly measure the shape of something as vast as the entire cosmos? The answer lies in the oldest light we can see. The patterns of hot and cold spots in the cosmic microwave background are like a cosmic ruler. In a flat universe, the vast majority of these ripples should appear at a specific angular size on the sky, about 1 degree across. When satellites like Planck mapped this ancient light with phenomenal precision, that is exactly what they found. The data overwhelmingly points to a universe that is flat, or so nearly flat that we cannot detect any curvature. This profound finding tells us that the combined density of dark matter, dark energy, and ordinary matter adds up to that precise critical value, a cosmic balancing act of astonishing accuracy. The implications of this flatness are staggering. It strongly suggests that our universe is truly infinite. Beyond the horizon of our observable cosmos, space likely continues without end, filled with more galaxies, more stars, and potentially more versions of everything we know. This is a humbling and almost incomprehensible thought. A spherical universe would have been a cozy, finite place, a cosmic globe, but a flat universe offers no such comfort. It is an endless expanse. This geometry also impacts the possibility of seeing ghosts in the sky. In a finite, spherical universe, light could wrap all the way around, meaning we might see multiple images of the same supercluster of galaxies in different directions, like a hall of mirrors on a cosmic scale. In our flat, likely infinite universe, such wraparound effects are not expected, leaving each galaxy as a unique island in the vastness. The flat shape we have measured is a direct consequence of the universe's violent infancy, that explosive period of inflation which stretched the primordial cosmos to such an immense scale that any initial curvature was smoothed away, leaving behind the flat plane we inhabit today. This geometry is inextricably linked to the dark energy driving the acceleration, locking the universe into a specific, expansive future. Pinpointing the age of our universe requires reading multiple cosmic clocks, all of which seem to agree on one remarkable number, 13.8 billion years. The most fundamental technique is to wind the expansion of the cosmos backward in time. By measuring how fast the universe is expanding today, a value known as the Hubble constant, and then factoring in how that expansion rate has been altered over time by the gravitational pull of matter and the repulsive push of dark energy, we can calculate how long it has taken for all the galaxies to reach their current separations. It is like tracking the path of a bullet back to the moment it left the gun's barrel. This method relies on incredibly precise measurements of both the distances and velocities of far-off galaxies. Astronomers use certain types of stars and supernova as standard candles, objects with a known intrinsic brightness. By observing how dim they appear to us, we can calculate their exact distance. Combining this with the redshift of their light, which tells us how fast they are receding, gives us the Hubble constant. When we run the cosmic film in reverse, accounting for all the forces at play, the expansion converges to a single point of infinite density 13.8 billion years ago. This timeline is powerfully confirmed by another, completely independent clock, the cosmic microwave background. The Planck satellite's detailed map of this ancient afterglow acts as a snapshot of the infant universe. By analyzing the subtle patterns in its temperature, scientists can determine the universe's ingredients, the amounts of ordinary matter, and dark energy with exquisite precision. Plugging these values into our cosmological models yields an age, and it is the same number, 13.8 billion years. This is a stunning cross-check, using the baby picture of the universe to verify the story told by its current expansion. We can also look closer to home, to the oldest stars in our own galaxy, to test this timeline. Globular clusters are dense, spherical swarms of millions of stars that orbit the outskirts of the Milky Way. They are cosmic relics containing some of the first stars to form after the Big Bang. By studying the colors and brightness of the stars in these clusters, astronomers can determine their age. The oldest among them are consistently dated to be around 13.5 billion years old. This provides a powerful lower limit. The universe must be older than the stars within it. Another local method involves observing the cooling of white dwarf stars. White dwarfs are the dense, Earth-sized cores left behind when Sun-like stars die. They have no source of internal energy, so they simply glow with the leftover heat from their earlier lives, slowly cooling down over billions of years. By measuring the temperature of the oldest white dwarfs in our galaxy, we can estimate how long they have been cooling. These cosmic embers also point to an age that aligns perfectly with the other methods. This remarkable convergence of evidence, from the large-scale expansion down to the cooling of stellar corpses, gives us tremendous confidence. When entirely different lines of inquiry, each with their own potential for error, all point to the same moment of origin, it tells us our standard model of cosmology is fundamentally sound. We are living in a universe that has been evolving for 13.8 billion years. A timeline written in the light of receding galaxies, the faint whisper of creation, and the slow, steady fading of ancient suns. That spectacular burst of expansion, cosmic inflation, demands a driving force. The leading candidate is a hypothetical entity known as the inflaton field. Picture a field not of grass, but a kind of energy that permeated every point in the newborn cosmos. This inflaton field found itself trapped in a state of false vacuum, a high-energy configuration that was not its true, stable minimum. In this peculiar state, the field's immense energy density generated a powerful repulsive gravity, an anti-gravity effect that violently pushed space itself apart. This was the engine of inflation, a single scalar field driving the universe to double in size over and over again in fractions of a second. but this phase could not last forever. Like a ball resting on a high plateau, the inflattened field was unstable. It eventually began to roll down its energy hill, oscillating around the bottom of its true vacuum state. As it oscillated, it decayed spectacularly. In a process called reheating, the immense potential energy stored in the inflattened field was converted into a raging firestorm of particles and radiation. This was the moment the universe truly became hot, flooding the cosmos with the quarks, electrons, and photons that would form the primordial plasma. This transition from a cold, expanding void driven by the inflaton to a hot, dense universe is a cornerstone of the theory. Yet the exact nature of the inflaton field remains one of cosmology's great puzzles. Was it a single, fundamental field or a composite of several? Various models of inflation propose different shapes for that energy hill, leading to different durations and intensities for the inflationary burst. These subtle differences are not just academic, they leave distinct fingerprints on the cosmos. The most crucial prediction of any inflation model is the pattern of the primordial quantum fluctuations that got stretched to cosmic size. During inflation, the quantum jitter of the inflattened field itself was magnified into tiny variations in density. The specific model of inflation determines the statistical properties of these ripples, their strength, and how they are distributed across different scales. This is where theory meets observation. Our most powerful tool for testing these models is the cosmic microwave background. The tiny temperature variations we see in that ancient light are the direct descendants of those inflated quantum seeds. By mapping these fluctuations with incredible precision, using telescopes like Planck, we can measure their properties. How much more strongly do large patches fluctuate compared to small ones? Is the distribution perfectly random, or are there subtle correlations? The answers to these questions allow us to rule out some inflationary models and support others. The search for a unique signature, a telltale pattern called primordial gravitational waves, is the next frontier. These waves, if detected, would be a direct probe of the energy scale of inflation, offering our clearest glimpse yet into the physics that drove the universe's most dramatic growth spurt. Those first seconds were a frantic, searing transformation where the universe forged its fundamental identity. To understand this, we must travel down a timeline of incredible brevity, where each fraction of a second brought a radical new phase of existence. At time zero, the moment of the Big Bang singularity, our known physics fails. But by the time the universe is just 10 to the minus 43 seconds old, we enter the first era where we can even begin to apply theoretical concepts, the Planck epoch. This is an almost unimaginably brief flicker, but it was a realm of pure potential. Here, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were believed to be unified into a single superforce. The energy was so immense that spacetime itself was likely not smooth, but a chaotic, boiling quantum foam where concepts of before and after may have had no meaning. As the universe expanded and cooled past this mark, gravity was the first force to separate, breaking from the unified superforce and setting the stage for the structure of the cosmos to eventually form. The next great transition occurred at around 10 to the minus 36 seconds, with the end of the grand unification epoch. Here, the strong nuclear force split away from the electroweak force. This separation released an enormous amount of energy, potentially triggering the incredible inflationary expansion that shaped the cosmos. The universe was now a rapidly expanding, seething soup of the most elementary particles and energy. For a brief period, it was so hot that even the Higgs field, which gives particles their mass, could not act, meaning everything moved at the speed of light. As it cooled further, the electroweak force split into the electromagnetic and weak nuclear forces we know today. This established the four distinct forces that govern our reality. By the time the universe was a millionth of a second old, it was a dense, opaque ocean known as the quark-gluon plasma. quarks, the building blocks of protons and neutrons, and gluons, the particles that carry the strong force, zipped around freely in this primordial soup. You could not find a single proton or neutron because the energy was too high for quarks to stick together. Then, as the temperature dropped further, a pivotal moment occurred: hadronization. The universe cooled enough for quarks to become confined, binding together in groups of 3 to form the first stable protons and neutrons. This was the moment the raw ingredients for atomic nuclei were born from the chaos. Almost immediately after, another crucial event unfolded: neutrino decoupling. Neutrinos, those ghostly particles that barely interact with anything, were suddenly set free. The universe had become just transparent enough for them to stream outward unimpeded, creating a cosmic neutrino background that still permeates space today, a fossil even more ancient than the cosmic microwave background. The final act of these first seconds was the nucleosynthesis we explored earlier, where those newly minted protons and neutrons began to fuse into the first atomic nuclei, primarily hydrogen and helium. Every single step in this explosive sequence was dictated by the precise conditions of temperature and density, the specific way the forces broke symmetry, the exact ratio of matter to antimatter that survived, the timing of hadronization. All of it was locked in during these initial moments. The properties of our universe, its geometry, its composition, and its potential for future complexity were irrevocably determined in that first furious second. This foundational architecture immediately raises a deeper puzzle about the very laws that govern this incredible transformation. Why do the fundamental constants possess the exact values that made this intricate cosmic evolution possible? The precise cosmic recipe that emerged from the first second seems almost too perfect. This leads us to a mystery that strikes at the heart of physics itself. How did the laws of the universe come to be? We take for granted that nature follows rules, but we rarely stop to ask why these specific rules. Why is the speed of light exactly 299,792,458 meters per second? Why does gravity pull with the exact strength it does? The truly startling fact is that these numbers are not arbitrary. They appear to be exquisitely fine-tuned for the existence of complex life. If we could adjust the cosmic dials even slightly, the results would be catastrophic. If the strong nuclear force, the glue holding atomic nuclei together, were just 2% stronger, protons would bind so tightly that hydrogen would be rare and stars would burn out rapidly. If it were 2% weaker, atomic nuclei could not form at all, leaving the universe as a boring soup of hydrogen. If gravity were a bit stronger, stars would be smaller and burn through their fuel in millions of years, not billions, leaving no time for planets to cool and life to evolve. If the mass of the electron were different, the delicate chemical bonds that form complex molecules would fail. It is as if the universe was built on a knife's edge, with dozens of fundamental constants all perfectly balanced to allow for galaxies, stars, planets, and ultimately us. This is the fine-tuning problem, and it demands an explanation. One possibility is the anthropic principle. In its simplest form, it states that we observe a universe with these particular laws because they are the only ones that allow for observers to exist. We could not possibly be asking these questions in a universe that could not produce us. It is a logical, if somewhat passive, answer. A far more expansive explanation arises from the idea of the multiverse. If our universe is just one bubble in an infinite cosmic froth, then every possible set of physical laws is realized somewhere. Most of these universes would be sterile, empty, or stillborn. But in a rare few, the numbers would line up perfectly by pure chance. We simply live in one of the lucky ones. String theory lends mathematical weight to this idea, suggesting a landscape of perhaps 10 to the 500 possible vacuum states, each corresponding to a universe with different laws and constants. Our home is just one point in this unimaginably vast landscape of possibilities. Yet another perspective suggests these laws may not be truly fundamental at all. Perhaps they are emergent properties arising from a deeper, more primitive level of reality we have not yet discovered. The way temperature and pressure emerge from the collective motion of countless molecules, the laws of gravity and electromagnetism might emerge from the complex interactions of something more basic, like the geometry of spacetime itself at the quantum scale. This idea is still speculative, but it offers a thrilling possibility that the elegant rules governing our cosmos are not the final word, but merely the surface appearance of a much deeper, hidden reality. The universe's grand architecture can be traced back to the smallest of all possible scales, to a ghostly dance within the void. According to quantum mechanics, empty space is not truly empty. It is a seething, restless sea of energy, a place where the very concept of nothingness breaks down. Here, pairs of virtual particles and their antiparticles constantly flicker into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing back into the energy loan that created them. This ceaseless, probabilistic activity is known as quantum fluctuation. It is a fundamental property of reality, confirmed by subtle effects we can measure in the lab. In the tranquil void of interstellar space, this quantum jitter is usually inconsequential, a microscopic froth with no large-scale impact. But in the first fraction of a second of the universe, during the explosive period of cosmic inflation, something extraordinary happened. The fabric of spacetime was stretched faster than the speed of light. Those minuscule quantum fluctuations, these tiny wrinkles in the energy field, were suddenly magnified to cosmic proportions. They were no longer microscopic blips, but were inflated into vast regions of slightly higher and lower density spread across the entire infant cosmos. This is the breathtaking link between the quantum world and the cosmos we see today. Those tiny, random imperfections, born from the ghostly dance of virtual particles, became the gravitational seeds for all structure in the universe. They are the very reason anything exists at all. When we look at the cosmic microwave background, the map of those first density variations, we are seeing the amplified imprint of quantum fluctuations. The slightly denser patches imprinted on that ancient light had just a little extra gravitational pull. Over hundreds of millions of years, they acted as anchors, drawing in surrounding dark matter and gas. What began as a microscopic quantum ripple grew, snowballing under gravity's relentless pull, first into vast webs of dark matter, then into the first protogalaxies, and finally into the stars and planets we see today. Every galaxy cluster, every swirling spiral, every star and planet is the direct descendant of a quantum fluctuation stretched across the sky during the universe's most violent growth spurt. This means the distribution of galaxies across the cosmos is not truly random. It is a fossilized record of the universe's quantum mechanical origins. The grand tapestry of the cosmos, with its great walls and vast voids, was woven from threads of quantum uncertainty. This profound connection forces us to reconsider our place in the universe. The carbon in our bodies, the iron in our blood, the very planet we stand on, all originated from the gravitational collapse of a gas cloud that itself was born from one of those infinitesimal quantum seeds. We are not just living in a universe that permits quantum mechanics, we are living in a universe that was built by it. The quest for a multiverse pushes our observational powers to their absolute limit. If other universes exist in a vast, eternal cosmic foam, forever separated from our own by an ever-widening gulf of inflating space, can we ever hope to find a trace of them? Some scientists believe the answer might be yes, and they are scrutinizing our most ancient cosmic relic for signs of a collision. The prime candidate for this evidence is the cosmic microwave background. This afterglow is the universe's first and largest possible canvas, a snapshot of the entire sky when the cosmos was just 400,000 years old. Theorists suggest that if our universe is just one expanding bubble in a multiverse, it might have bumped into a neighboring bubble in the distant past long before the CMB was released. Such a cosmic fender bender would have sent powerful shockwaves rippling through the fabric of our infant universe. These waves would have left an imprint, a kind of bruise or a distinctive circular pattern of altered temperature in the cosmic microwave background. Researchers have meticulously scanned the Planck satellite's data, searching for these telltale scars. They have identified a few intriguing, large-scale anomalies, like a mysterious cold spot and unexpected asymmetries in the temperature fluctuations. While fascinating, none of these have yet risen to the level of definitive proof, as they could also be statistical flukes or the result of more mundane astrophysical processes. Another potential signature lies in the large-scale structure of the universe itself. The gravitational influence of a nearby universe could, in theory, create a strange tug on the distribution of galaxies, leaving a vast, improbable imprint in the cosmic web. Finding such a pattern would be like discovering a fingerprint on a window pane, suggesting something immense exists just on the other side. The challenge is that any signal from another universe would be incredibly faint, buried under eons of subsequent cosmic evolution and masked by the dominant signatures from our own universe's inflation. The very laws of physics as we know them may also conspire against us. If other universes have different fundamental constants, the forces that govern them might prevent any information or energy from crossing the boundary into our realm. We are essentially looking for a message written in an alien physics, sent across a divide that may be fundamentally uncrossable. This makes the search for a multiverse one of the most thrilling and controversial pursuits in modern cosmology. It is a grand exercise in scientific speculation, where the potential reward is the ultimate expansion of reality. But the evidence remains tantalizingly just out of reach, whispering to us from the edges of our observable sky. That moment of transparency arrived like a sudden clearing in a cosmic fog. For nearly 400,000 years, the universe was an impenetrable, glowing plasma, a searing soup where electrons and protons roamed free, constantly scattering the intense light that filled every corner of space. It was a brilliant but blinding era, a world where you could not see your hand in front of your face because light could not travel in a straight line for more than a tiny fraction of an inch before bouncing off another charged particle. Then a profound and universal shift occurred, a phase change known as recombination. As the cosmos continued to expand and cool, it finally dropped below a critical temperature of about 3,000 degrees. Suddenly, the frantic dance of charged particles could slow down. Electrons, which had been bouncing freely for eons, were now captured by protons, combining to form the first stable, neutral atoms of hydrogen. This was the moment the fog lifted. The photons, the particles of light that had been trapped in that relentless scatter, were suddenly set free. With no more free electrons to bounce off of, they could finally stream across the universe in straight line. This great liberation of light is the event whose aftermath we see today as the cosmic microwave background. That ancient glow is the direct snapshot of the universe at the precise instant it became transparent. This was not a gradual dimming, but a sudden and dramatic transition. One moment the cosmos was a blinding, opaque fireball. The next, it was a dark, transparent expanse filled with a uniform, fading light and a thin, simple gas of hydrogen and helium. This epoch of recombination marked a fundamental divorce between matter and radiation. For the first time, the universe's contents were no longer locked in a tight, searing embrace. Matter could now begin to clump together under gravity without being constantly buffeted by intense radiation pressure. The light, now free, simply traveled, cooling and stretching with the expanding universe over billions of years to become the faint microwave whisper we detect today. This transition plunged the cosmos into its next great chapter, the cosmic dark ages, a time of profound silence and darkness that would last until the first stars ignited. While photons were trapped in the searing plasma, Another, far more elusive particle was already streaming freely through the cosmos. Neutrinos are the universe's ghost particles, produced in staggering numbers within the very first second after the Big Bang. They are so incredibly weakly interacting that they can pass through light years of lead without a single collision. This aloof nature meant they were the first to decouple from matter, breaking free from the primordial soup a mere second after the beginning, long before the cosmic microwave background was set loose. For a brief period, these countless neutrinos dominated the energy budget of the universe, forming a dense sea of radiation that exerted its own powerful influence on the cosmos. Their collective gravity and pressure acted as a drag on the growth of the very first structures. The tiny ripples that would one day become galaxies had to fight against this relentless, invisible wind of ghost particles, which smoothed out the smallest density fluctuations and set a minimum scale for the first clumps of matter to form. This cosmic neutrino background is still all around us today, a fossil even more ancient than the microwave afterglow. Billions of these primordial neutrinos are passing through your body every second, a whisper from the universe's first moment of existence. Yet detecting this background directly is a monumental challenge, as these ghosts interact so feebly with ordinary matter that they slip through our most sensitive instruments unseen. The key to unlocking their secrets lies in measuring their mass. For decades, neutrinos were thought to be massless, but we now know they have a tiny, non-zero mass. This discovery alone has profound implications. Even a minuscule mass, when multiplied by the unimaginable number of neutrinos in the cosmos, means they contribute to the overall mass budget of the universe, influencing its expansion and the formation of its largest structures. Current experiments are trying to pin down this elusive value, which could help us understand why the universe looks the way it does and perhaps even point toward new physics beyond our current models. These silent, pervasive ghosts from the dawn of time may hold the final piece to the puzzle of our cosmic origins. The evidence for an expanding universe is written in the very light from distant galaxies, a cosmic fingerprint discovered less than a century ago. In the 1920s, astronomer Edwin Hubble was studying faint, fuzzy patches of light known then as nebulae. Using the powerful new 100-inch Hooker telescope at Mount Wilson, he made a pair of stunning observations that would change everything. First, he confirmed that many of these nebulae were not clouds within our own Milky Way, but were entire island universes, galaxies in their own right, lying far beyond our own. This immediately made the cosmos a much larger place. Then he did something even more profound. By analyzing the light from these galaxies, he noticed a pattern. The light from almost all of them was shifted toward the red end of the spectrum. This redshift is a familiar effect, similar to the way the pitch of a siren drops as a police car speeds away from you. The sound waves are stretched, lowering their frequency. In the same way, the light from a receding galaxy is stretched as it travels through an expanding universe, shifting its color toward red. The truly revolutionary part came when Hubble combined these redshift measurements, which indicated velocity, with estimates of the galaxy's distances. He found a direct and simple relationship. The farther away a galaxy is, the faster it appears to be receding from us. This is Hubble's law, a cornerstone of modern cosmology. It means we live in an expanding cosmos where space itself is stretching, carrying galaxies along with it like raisins in a rising loaf of raisin bread. As the dough expands, every raisin sees all the other raisins moving away, with more distant ones receding faster. This expansion is not galaxies flying through a static space, it is the fabric of space between them growing. The cosmological redshift is the direct result of this stretching of spacetime, a permanent record of the universe's ongoing growth. The discovery of the cosmic microwave background provided the ultimate confirmation. That faint afterglow is the cooled and stretched remnant of the universe's hot, dense beginning, the natural starting point for the expansion we see today. For decades, measuring the rate of this expansion, known as the Hubble constant, has been a primary goal of astronomy. Yet today, this very measurement has plunged cosmology into a fascinating crisis. We have two supremely precise ways to measure the expansion rate. One method uses the cosmic distance ladder, building from nearby stars to distant supernova to pin down the Hubble constant. The other method uses the detailed blueprint of the cosmic microwave background from the Planck satellite, which tells us what the early universe was like, and then uses our standard model of cosmology to predict what the expansion rate should be today. These two methods, one a direct measurement of the modern universe and the other a prediction based on its ancient past, should agree, but they do not. They disagree by a small but stubborn amount. This discrepancy is known as the Hubble tension. It is a tantalizing clue that our standard model of the universe, for all its success, might be incomplete. Perhaps dark energy is not a constant but is evolving. Maybe there is a new, unknown type of particle or field that influenced the early cosmos. Or perhaps our understanding of gravity itself needs a subtle revision. The expanding universe is not just a settled fact, it is an active frontier, and its precise speed may be the key that unlocks the next great revolution in our understanding of reality. Our universe was born from a singularity where the known laws of physics break down, but what if we had a theory that could peer into that very moment? One of the most ambitious candidates for this ultimate theory is string theory, a framework that seeks to unify all forces and particles into a single, elegant description of reality. Its core idea is a beautiful simplification. The fundamental constituents of the universe are not zero-dimensional points, but unimaginably tiny, vibrating loops of energy or strings. Just as a single violin string can produce different notes depending on how it vibrates, each distinct vibration of a fundamental string corresponds to a different particle. One vibration gives us an electron, another a quark, and another the particle of light, the photon. In this symphony of strings, every particle and every force emerges from the same basic ingredient. This elegant concept naturally includes gravity, with the graviton, the hypothetical carrier of the gravitational force, arising as just another vibrational mode of a string. For the first time, a theory promises to weave Einstein's general relativity, which governs the cosmos, together with the quantum mechanics of the very small. But this unification comes with a startling requirement: extra dimensions of space. For the mathematics of string theory to work consistently, it demands not just the 3 spatial dimensions we experience, but a total of 10 or more. These extra dimensions are thought to be curled up or compactified into a space so incredibly small that they are hidden from our perception. Much like a garden hose appears as a one-dimensional line from a distance, but reveals its circular second dimension upon closer inspection. How does this help us understand the Big Bang? String theory provides a new set of tools to describe the extreme conditions of the initial singularity. It suggests that at those incredible energies and temperatures, the universe was a landscape of these vibrating strings and their higher dimensional counterparts called branes. One compelling scenario for the universe's birth is the ekpyrotic model, which proposes that our Big Bang was not a singularity, but the result of a collision between 2 of these giant branes moving through a higher dimensional space. The immense energy of that collision, reverberating through our 3-dimensional brain, could have created the hot, dense state we identify as the beginning of our cosmic timeline. This offers a vision of a cyclic universe where brane collisions lead to successive Big Bangs. The mathematical elegance of string theory is undeniable, and it has produced profound insights into the nature of black holes and quantum gravity. Yet it remains a theory in search of experimental confirmation. The energy levels required to probe the string scale are far beyond the reach of any particle accelerator we could ever build. Furthermore, string theory does not yield a single, unique prediction for our universe, but a vast landscape of possible solutions, each with different physical laws and constants. This very richness makes it difficult to derive specific, testable predictions that could confirm or refute it. For now, string theory stands as a magnificent and powerful piece of mathematical architecture, a potential key to the universe's deepest secrets, but one that remains frustratingly just beyond our empirical grasp. This uniformity across billions of light-years presents a profound riddle. Why does the universe look the same in every direction, with the cosmic microwave background displaying an almost identical temperature from one side of the sky to the other? Distant regions on opposite horizons have never exchanged a single photon of light or a ripple of information, according to the standard Big Bang timeline. There simply has not been enough time for any signal, limited by the speed of light, to have traveled between them to establish this thermal equilibrium. It is as if you walked into a vast, ancient library and found that every single book, even those written in completely isolated rooms, contained the exact same words on every page, with no possible way for the authors to have communicated. This is the horizon problem, a deep flaw in the original Big Bang model that pointed to a missing chapter in our cosmic history. The solution required a mechanism that could connect these distant realms before blowing them apart. Cosmic inflation provides this elegant fix. Before the period of explosive expansion, the entire observable universe was crammed into a tiny, subatomic volume. This microscopic patch was so small that it had ample time to reach a uniform temperature, just as a hot cup of coffee naturally stirs itself to an even warmth. Then, inflation acted like a cosmic zoom lens, stretching this tiny, thermally equilibrated speck to a size larger than our entire visible cosmos in a fraction of a second. Those regions that now lie on opposite sides of our sky were once cozy neighbors, close enough to exchange energy and settle into balance. The superluminal expansion of space itself then ripped them apart, placing them far beyond each other's cosmic horizons while preserving their identical properties. This is why inflation is not just an interesting add-on to cosmology, but a foundational pillar. It explains the large-scale smoothness of the cosmos while simultaneously planting the seeds for all future structure through quantum fluctuations. Without this initial period of unimaginably rapid growth, the universe would be a patchwork of disconnected domains, each with its own wildly different temperature and destiny, a chaotic and likely lifeless place. This perfect uniformity, the bedrock of our cosmology, might have a crack in its foundation. A strange and unsettling anomaly lurks within the pristine map of the cosmic microwave background. When scientists analyze the patterns in this ancient light, they find peculiar, large-scale asymmetries. For instance, the temperature fluctuations on one half of the sky appear slightly different from those on the other, and there seems to be a curious alignment of the largest waves along a specific cosmic axis, a direction some researchers have whimsically, yet ominously, nicknamed the axis of evil. This moniker reflects how deeply this finding disturbs a core principle of modern cosmology, the assumption that the universe is isotropic, meaning it looks the same in every direction. If true, this anomaly suggests a preferred direction in the cosmos, a cosmic north that should not exist. So what could be causing this strange signature? The most conservative explanation is that it is not real at all, but merely a systematic error. Perhaps our instruments, or the way we process the data to subtract the foreground glow of our own Milky Way galaxy, has inadvertently imprinted this peculiar pattern onto the map. Despite rigorous checks, this possibility can never be entirely ruled out. If the effect is real, however, the implications are profound. It could be a relic from before inflation, a fossilized imprint of the universe's chaotic, pre-inflationary geometry. Imagine inflation starting not in a perfectly smooth state, but in a cosmos that already had a slight preferred direction, a primordial wrinkle that was then stretched across the entire sky. Another, even more mind-bending possibility is that this axis marks the direction of a gravitational tug from something outside our observable universe. Perhaps our cosmos is not an isolated bubble, but one of many in a vast multiverse. The axis of evil could be the faint bruise left by a collision with a neighboring universe in the distant past, a cosmic fender bender whose echo is frozen in the first light. While the evidence is not yet strong enough to overthrow our standard models, the mere existence of this puzzle is a powerful reminder that cosmology is a living, breathing science. Our maps of the cosmos are not yet complete, and the universe may still hold profound surprises about its fundamental nature. The existence of supermassive black holes in the infant cosmos presents a glaring cosmic contradiction. We now observe these gravitational giants weighing billions of suns, shining from the universe's first few 100 million years. According to conventional wisdom, a black hole should form from the collapse of a single massive star, starting with a mass of only a few tens of suns. To grow so immense so quickly, it would have to eat at a ferociously unsustainable rate for its entire existence. It is like finding a fully grown ancient redwood tree sprouting from a crack in the pavement just days after the soil was laid. How could such colossal objects emerge almost immediately after the first stars flickered to life? The answer may lie in a completely different kind of birth, one that bypasses stars entirely. This is the theory of direct collapse. Imagine a pristine cloud of primordial hydrogen and helium gas, untouched by the heavy elements forged in stellar furnaces. Without these elements to help it cool and fragment, this vast cloud does not break apart into many small stars. Instead, under the immense pull of its own gravity in the heart of a young protogalaxy, the entire cloud begins to collapse as a single, monstrous unit. It skips the star-forming stage altogether, plummeting inward until it reaches a critical density and directly forms a black hole. This is not a stellar corpse, but a primordial behemoth, a heavy seed black hole born with a mass tens of thousands of times greater than our Sun. This gives it a tremendous head start, a gravitational anchor of immense power from day one. The alternative theory suggests that smaller, stellar mass black holes could have grown with astonishing speed. In the dense, chaotic cores of the first galaxies, gas was plentiful. A small black hole could have feasted continuously, pulling in vast amounts of material in a frenzied accretion disk that glowed with the light of billions of stars. These early black holes might have also merged together frequently, rapidly building mass through a series of violent cosmic collisions. This creates a classic chicken and egg problem with the galaxies themselves. Did the supermassive black hole form first, its gravity helping to pull together the galaxy around it? Or did the galaxy form first, its dense core providing the perfect nursery for a black hole to rapidly grow? The most likely answer is a co-evolution, a symbiotic relationship where the growing black hole and the budding galaxy fed each other's growth in a tight, dynamic feedback loop. The arrival of the James Webb Space Telescope is now shedding brilliant new light on this ancient mystery. Its infrared eyes are peerless at spotting the most distant quasars, the dazzling beacons powered by these early supermassive black holes. Webb is not just finding them, it is studying their environments, measuring their masses with unprecedented precision, and probing the galaxies they inhabit. Early data suggests that black holes in the early universe were not just massive, but often disproportionately so compared to their host galaxies, a clue that their formation pathways were fundamentally different from those in the modern cosmos. Each new observation brings us closer to understanding whether direct collapse, rapid growth, or some other exotic mechanism was the primary architect of the universe's first gravitational giants. That faint cosmic murmur from the Big Bang carried the blueprints for the entire architecture of reality. If you could step back and view the universe on the largest possible scale, you would not see a random scattering of galaxies. Instead, you would witness an intricate web-like structure of breathtaking grandeur and complexity. This is the cosmic web, the true skeleton of the cosmos. Gigantic filaments of galaxies, millions of light years long, twist and curve through the void, connecting at dense nodes where vast clusters of thousands of galaxies swarm together. Between these brilliant strands lie the cosmic voids, immense deserts of near emptiness so vast that a single one can span hundreds of millions of light years. This is not a static sculpture, but a dynamic, evolving entity, and its origin story is written in the first moments of time. The seeds for this cosmic metropolis were those tiny quantum fluctuations from the inflationary epoch, the microscopic wrinkles in space-time that were stretched to cosmic proportions. In the early universe, dark matter began its work. Unaffected by the pressure of light, this invisible scaffolding started to collapse under its own gravity first, forming a vast, diffuse web of invisible halos and tendrils. Then, ordinary matter, the hydrogen and helium gas, began to feel the irresistible pull. It flowed like water down a hill, streaming along the dark matter filaments, channeling toward the intersections where the gravitational wells were deepest. The galaxies we see today are not the web itself, but the glittering light strung along its invisible threads, tracing out a pattern that was forged in the dark. Supercomputer simulations of this process are a thing of beauty. They start with a nearly smooth distribution of particles, representing the dark matter after the Big Bang. As the simulation runs, representing billions of years of evolution, gravity works its magic. The particles slowly clump together, first into tiny specks, then into larger knots, all connected by ever-lengthening streams of matter. The final result looks uncannily like a neural network or a froth of soap bubbles, a cosmic sponge on a scale beyond human comprehension. This is not just a theoretical fantasy. Massive galaxy surveys, like the Sloan Digital Sky Survey, have painstakingly mapped the positions of millions of galaxies across the sky. When their locations are plotted in 3 dimensions, the result is stunning. The galaxies align along delicate filaments and walls, confirming the web-like structure predicted by the simulations. We are literally drawing the map of the cosmos, and it reveals a web of astonishing order born from initial chaos. Mapping this cosmic web is one of the most powerful tools we have for understanding the universe's hidden components. By studying how quickly the filaments formed and how massive the clusters became, we can weigh the dark matter. The way the web stretches and evolves over time tells us about the strength of dark energy, the force that is pushing the universe apart. The cosmic web is a frozen record of the entire history of cosmic evolution, from the first quantum whisper to the great dark energy-driven expansion of today. We are living inside the greatest structure imaginable, a web whose threads connect every galaxy, every star, and every one of us to the primordial dawn. The solid reality you perceive around you, the 3-dimensional world of depth and volume, might be the ultimate cosmic illusion. This is the radical premise of the holographic principle, a concept so profound it suggests our universe could be a hologram. The idea does not come from science fiction, but from the deep physics of black holes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, a measure of its information content, is not proportional to its volume, but to the surface area of its event horizon. It was as if all the information about everything that fell into the black hole was not stored within its vast interior, but was somehow encoded pixel by pixel on its 2-dimensional boundary. This discovery led to the holographic principle, which boldly proposes that this is a universal rule. The total information content of any region of space, including our entire cosmos, can be fully described by bits of information stored on its outer surface. In this mind-bending view, our rich 3-dimensional reality, with its galaxies, stars, and planets, is a projection, a holographic image generated from a cosmic code written on a distant 2-dimensional shell. Think of watching a three-dimensional movie on a flat, two-dimensional screen. The image has depth and perspective, but all the data required to create that illusion is contained in the flat pixels of the screen. The holographic principle suggests our universe operates in a similar way. We are living inside the projection. This concept finds a natural home in string theory, where the mathematics often describes our world as a hologram. One of the most concrete realizations of this idea is the anti-de Sitter conformal field theory correspondence, a powerful duality that provides a complete dictionary for translating between a gravitational theory in a bulk volume of space and a quantum field theory without gravity living on its boundary. This means that a phenomenon that is incredibly difficult to calculate in a gravitational, three-dimensional world can be perfectly translated into a simpler, non-gravitational calculation in one less dimension. It is a theoretical tool of immense power, suggesting that the fundamental degrees of freedom of our universe are not the particles and forces we see, but are encoded on a remote, lower-dimensional surface. If true, this principle would solve one of the most vexing problems in theoretical physics, the conflict between general relativity and quantum mechanics, by showing they are two different descriptions of the same underlying reality. The implications for the origin of the universe are staggering. The Big Bang singularity might not have been a point in three-dimensional space, but the moment when a lower-dimensional surface began to project our reality into existence. The smooth fabric of space-time we experience would then be an emergent property, a collective effect of the intricate quantum interactions happening on that fundamental two-dimensional screen. While this remains a highly speculative frontier of theoretical research, it forces a complete re-evaluation of what is real. It challenges the very notion that space and dimension are fundamental, suggesting they are derived concepts, an elegant and convincing illusion born from a deeper, simpler layer of reality. Despite our incredible journey through cosmic history, the universe remains deeply mysterious. The grandest unsolved questions are not just gaps in our knowledge, but chasms that challenge the very foundations of physics. We are still utterly confounded by the true nature of dark matter and dark energy, those twin phantoms that make up 95% of reality, yet remain completely invisible to our instruments. We have no idea what dark matter particles are, and we are equally baffled by dark energy's repulsive force. Is it a constant feature of the vacuum, or a dynamic field that could change over time, sealing the universe's ultimate fate in a big freeze, a big rip, or something else entirely? The origin of the universe itself is still a profound enigma. Our physics simply breaks down at the initial singularity, leaving us to wonder what, if anything, came before the Big Bang, and whether our cosmos is one of many in a vast, perhaps infinite, multiverse. The puzzle of baryogenesis, the mystery of why any matter survived the great annihilation with antimatter, remains unsolved. We know a cosmic crime occurred that left us with a universe of something rather than nothing, but we have yet to catch the culprit in the act. All of these mysteries point toward a single, monumental goal, the quest for a theory of quantum gravity. We desperately need a framework that can unite the cosmic realm of general relativity with the subatomic world of quantum mechanics. Without it, we cannot truly understand the universe's first moment or the interior of a black hole. Other pressing questions abound. What was the precise nature of the inflationary field that blew up the universe, and what brought that incredible expansion to an end? Are the fundamental constants truly constant, or could they change over time, subtly altering the laws of physics across the cosmos? The existence of the multiverse is perhaps the most speculative yet far-reaching of all these frontiers. Is our universe just one bubble in an eternal cosmic froth? And if so, could we ever find evidence for these other realms? Cosmology is far from a finished science. It is a living, breathing field of discovery where every answered question peels back a layer to reveal new, deeper mysteries beneath. This relentless curiosity is what drives the next generation of colossal telescopes, sensitive underground detectors, and ambitious space missions. They are not just instruments, they are time machines and cosmic detectives, built to read the faintest whispers from the dawn of time and to finally illuminate the dark corners of our reality. Our journey through 30 cosmic questions reveals a universe both magnificent and deeply mysterious. We have traveled from the singularity's first flash to the accelerating expanse shaped by dark energy, from the quantum seeds of galaxies to the silent grip of dark matter. It is astounding to realize how much we have uncovered, piecing together a cosmic history spanning 13.8 billion years. Yet for every answer, a dozen new questions emerge from the void. The true nature of dark matter and dark energy remains elusive. We still do not know what triggered the Big Bang or if our universe is one of countless others in an infinite multiverse. The quest to understand our cosmic origins is far from over. It is one of humanity's greatest and most humbling adventures. It connects our most profound curiosity to the fundamental nature of reality itself. So we turn the final question to you. Which of these mysteries captivated your imagination the most? Was it the ghostly influence of dark matter, the mind-bending concept of the multiverse, or the sheer improbability of our own existence in a finely tuned cosmos? Let us know your thoughts in the comments below. If you enjoyed this exploration, please like, subscribe, and hit the notification bell so you can join us for our next deep dive into the wonders of the universe. The cosmos is waiting.